All right, last word problem. In fact, this one could have been done in the previous lessons. However, with this new idea of check and endpoint, let's look at one more example. Okay, the storage shed is to be built in the shape of a box with a square base. So, box, right? But the base is square. So that just means that it is x by x, right? We don't know what it is, but we'll just call it x. And we don't know anything about the height as y. It has to have a volume. So the volume in this case, length times width times height, is x times y, or x squared y. But we know the volume is 150 cubic feet. Okay. So we have that out of the volume. The concrete for the base costs $4 per square foot. So that's area, right? The base is $4 per square foot. And the roof costs $2. So the roof is $2 per square foot. And all the sides are $2.50. Well, how are we going to use that? Well, the total surface area to build this then, right? We have the bottom is x squared, so the surface area is x squared, but it's $4 per square foot. So it's x squared square feet. I don't know how many square feet, right? X times 4. Let's do the top. So the top is $2 per square foot, and the top is also x by x, so x squared. Now all the sides are the same, x times y, and they're $2.50 each, but we have 4 of those, right? 4 times x times y. So this reduces down to, let's see, 6x squared. And we'll just call this, we'll call it C actually, right? It's the cost. I know it's surface area, but we were multiplying by the cost. So this is C of x. Or actually just C, we'll call it just C now, because there is still a y, right? We're going to have to take care of that y here in a second. But this is our cost. Okay, plus 250 times 4 is 10xy. Now, we know we're trying to minimize the cost, right? The most economical shed, which means we're going to have to do derivative. But we have an x and y. That's when we have to come back here. Much easier to solve for y, right? Y is 150 over x squared. So now we could substitute that in there. Okay, let's start this at the top. C equals 6x squared plus 10x multiplied by 150 over x squared. That's y. Okay, that reduces to 6x squared plus one of those x's canceled. 10 times 150 is 1500 over x, or x to the negative 1. Okay, now we can start derivative. Set equal to 0. Derivative is 12x minus 1500 x negative 2. Set that equal to 0. 12x minus 1500 over x squared. So 1500 over x squared equals 12x. Multiply by x squared and divide 12. So we get x to the third. 1500 divided by 12. We're dividing both sides by 12, and we're timesing by x squared. So x to the third. So we get 125. Cube root it. That would be 5. And verify that this is a min. So let's come up here and look at second derivative. We would get 12 And then bring down the -2 is positive 3,000 x -3, which we really don't care. We care is it positive or negative. 12 plus 3,000 over x to the third. That's our second derivative, which x has to be positive, so I have a positive plus another positive is positive. Second derivative positive means concave up, which tells me it is in fact a min since the extreme min happens there. Alright, so we're good. It's definitely a relative min. I don't know about the absolute min, but it is a min. So if we have x, we still need y. Substitute back in, y is 150 over x squared, so over 25, so we get y is 6. So the dimensions in this case would be, the base is 5 by 5, and we're in feet, right? 5 feet by 5 feet by 6 feet tall. That's the base. Now, endpoints. This is a weird one, but you should always think about endpoints. There are no restrictions, right? So like the base, it could go all the way down to 0, but it can't be 0 because then I wouldn't have any length. So this does not have an endpoint. And then there is no restriction for the largest it could be, right? Because like, well, you might say, well, it can only be, we have 150, right? So, I don't know. It can only be so much because we have to be contained within the 150 cubic feet. But the thing is that even if this were 150 and this were 150 base, which it far exceeds the 150, we can make the height minimal, right? I mean, I'm talking like 0.1 or you know, something very minimal. So it's technically not bounded. Technically it could be as large as you want because then the height would be infinitely small. So this also doesn't have an endpoint. So there are no endpoints to check in this case. Some problems might have a further restriction in which it'd create an endpoint. Like it could only be, you know, let's say 5 feet wide or something, or 6 feet, whatever it is. If it gave you a restriction, that could be an endpoint, and you would have to check it to make sure you get the absolute max or absolute min, whichever one